Hi, welcome to another one of D's ADD videos. Today we're going to be talking about separable differential equations, and as the name implies, you shall be trying to separate like variables on the same side. That will be your goal here. So here is a sample problem that I just made up, and as you can see, the x's are on the same side as the y's over here, right? And this y should be over here with this dy. So the goal is to get all the d whatevers in the numerators and to get the variables on the same side. So to achieve that end, I shall be multiplying this dx on both sides, dividing that x squared plus 1 on both sides, and then finally dividing that y. So if I were to multiply both sides by dx, I would get x squared plus 1 dy dx equals y dx. Then I can divide both sides by x squared plus 1. And then after that, the x squareds plus 1's cancel on this side, and I'm left with, oops, that dx is no longer on this side, is it? We multiplied it on the other side. Should have caught that. Sorry, it's late making a video. So here on this side we're left with just dy, and on this side we have y dx over x squared plus 1. We're almost there. We got to get this y right here on the other side, so we can multiply by the reciprocal, divide by y, however you want to call it. It cancels on this side, and then we're left with 1 over y dy equals 1 over x squared plus 1 dx. So at this point we have all the variables on their respective sides. We're ready to integrate. The integral of 1 over y, typically we would bring this up to the numerator, change that to a negative exponent, and then add 1, but in this case we would get a 0, and when you integrate you would have to divide by a 0, and that's not possible, so that should clue you in to this is a special case. What do you derive to get 1 over y dy? Well, that would be an ln y. Alright, so that's just pure definition there. And then here on this side, you should remember your trig basic formulas. This is an arctangent. The integral of, here I'll do this in a different color so you know it's a rule, not part of the problem. Let's do this in red. So we have integral of dx over x squared plus a squared. That should equal 1 over a arctangent. Let's increase our space there. Arctangent x over a plus c. Right. So in this case our a is 1 and our x would be x itself. So plugging in we'd have 1 over 1 is just 1, so it'd just be arctangent of x over 1. Doesn't need to be written. And there would be our general solution to your differential equation. Why is it a general solution? Because we still have plus c. If I were to give you initial conditions, then you could solve for what c is. What are some conditions? For instance, I could tell you something like the initial values of y of pi over 4 equals 1. And what that should mean to you as a math student is that whenever x, because typically it's y of x, right? You usually see y of x, y is a function of x, and this x has now been replaced with a pi over 4, so that means that when x is pi over 4, y is equal to 1. So if we were to plug into that, we would get the ln of 1 is equal to arctangent. Oops, I goofed a little bit, I'm sorry. Let's change this to 1 itself, because I want the answer to be pi over 4. I want to take the arctangent of 1, so at that point we would have arctangent of 1 plus c. The beauty of making up a problem is you can change it around a little bit to suit your needs. So natural log of 1 is 0. Arctangent of 1 is asking me what angle has a tangent of 1, and that would be pi over 4. You can see where my brain associated the number pi over 4. It just got a little ahead of itself. So that means that c equals negative pi over 4. So we can now convert this general solution into a particular solution. If you remember, the general solution was ln of y is equal to arctangent of x plus c, and we just found out that c was negative pi over 4. So what this means is you can now call this a particular solution. I got a little ahead of myself again there. What I was doing is I was solving for y itself. This is what's called an implicit particular solution because we don't have it in terms of y equals. So if I take the e of both sides like I started doing a second ago, e and ln are inverses of each other and they would cancel on the left side, and then on the right side I'd be left with an explicit solution to my original differential equation. Okay, now where you can get tripped up, this concept's not too hard, is if you're not strong in your integration skills. So go back and review. It'll be well worth it if you take a little time to just refresh your skills. Differential equations can get really tedious at times, but it gets really difficult if you don't remember your calculus foundations. So I hope this was a beneficial video and taught you what you needed to know.